Hi everyone. Thank you to stay here to the second last talk of the day. I'm going to talk to you about Kubernetes, how leverage Kubernetes to run cluster Kubernetes. But I'm coming from Junction. Junction, we have a goal, which is trying to abstract our customers with all the complexity of run the clusters of Kubernetes. But it's just not a matter of the Kubernetes orchestrator anymore. There is a lot of different applications that Kubernetes need to run, or you can put on top of Kubernetes to make it really a extensive platform. This is like, no, come on. This is the cloud-native landscape, which cloud-native foundation is umbrella to ward different projects in the cloud-native space. And you can see here Kubernetes and other applications that used to run in the top of or below Kubernetes. So I took the risk yesterday to change the title of the talk, and I call it now Leverage Kubernetes to run a cloud-native platform. So one less shot. Let's start going through the points I'm going to touch today. So first is the analysis of the problem. Second, why we use Kubernetes to run clusters of Kubernetes. The third one, I will be talking a bit about operators and which operators do we have. The fourth is the release process, how we release our operators and the other components that we manage in the clusters. The fifth is the apps. So we also are starting to manage apps for our customer. I will talk a bit more later. And I will be closing the talk talking about observability and how we monitor all these pieces of the clusters to be successful running the platform. So let's start talking a bit about Kubernetes internal. Most of the talks has been explaining Kubernetes from the point of view of the user, but here I'm going to be more talking about the operator perspective. As you may know, Kubernetes cluster is composed by master or masters and workers, and we need different pieces running in both of those. In the master, we run the control plane components, which are the API, the powerful REST API that allows to manage our application, our workloads. And this API needs a database. Most of the times it's etcd, which is a distributed key value database, and is where all the information about the cluster is safe. Then next to the API, we have the controller manager, which is the group or the set of controllers that watch the Kubernetes resources that the user submit and work against the desired state of these components, these objects. Then we have the scheduler, which the main function of the scheduler is select in which pod is going to run your application, and also it schedule the pod when it's evicted from a worker. And the last one is the cloud manager, which is a new one that has been, I think, beta in the last release of Kubernetes. And has been stripped off from the controller manager process, and it wraps all the logic related with the cloud provider. So, for different take care of create the load balancer in your cloud provider. And this component is different, obviously, for the different clouds or environments that you run your Kubernetes. Then we have the workers, and where our applications will be running. And in these workers, we need two components. We need kubelet, which is the agent of Kubernetes, and it talks to the API to receive the different actions that it has to pursue. So, for example, it will create the container. It will make the health check-in of the application to see it's always running. It will help to provision the volumes or to allocate the network interface for your pods. And then next to this kubelet, we have the kube proxy, which mainly is load balancing the request of your services through the different pods that lives behind this service. But this is just one layer. This is the main layer that we manage, but there are different layers. The next one is the I layer. I like to call it like that, interface layer, because Kubernetes needs a set of requirements. It needs a container network, so our pods can talk one to each other. It needs, obviously, a container runtime, so container can be created. It needs also a storage solution, so we can provision our pods with some storage. Kubernetes community has created an abstraction there, so every of these components offer an interface, and each vendor can implement the interface. So Kubernetes is not having anymore, or is trying to not have anymore code that is from the vendor. So this is also a layer that we manage, and these different solutions that we run for each of those components have different moving parts, and some of them requires a backend database. So this is some things that we have to also take care. And then in the bottom of the cake, we will have the virtual machine or the physical machines, and we will have all the networking setup that has to be in place to make the virtual machines talk one to each other. And we also provide or provision all this infrastructure for our customers. And we need, for example, to make able the possibility of upgrade a virtual machine in your cloud provider, or change a networking setup because you are running something special in your cluster. So it's something also to take care of it. And then in the top of the Kubernetes layer, we have several components. I call it the core components. And these are the components that make functional the cluster. So for example, we have the ingress controller, which is the one who routes the traffic from outside the cluster to our services. We have the DNS server, which resolves the internal service names to pod IPs. We have the metric server that scrape all the containers and all the nodes stats and provide it to different abstractions of Kubernetes, like horizontal pod autoscaler. So that way we can scale our pods based on CPU or memory. And finally, we have the cluster autoscaler, which make it possible that the cluster expand or shrink depending on the capacity left. So finally, we have the customer workloads on top of, and we are not managing them. But as we didn't have enough things to manage, and we are seeing that our customers are running different tools in the top of the clusters, for example, to monitor their applications. So they run something like Prometheus or some Elasticsearch stack, or they want to use a service mesh or a CI/CD system. We decide to complicate our lives a bit more, and we have introduced right now managed apps. So we want to abstract also the complexity of these managed apps, or the complexity to run and operate these managed apps from the shoulders of our customers. And then this is getting more complicated when we have a customer which runs different clusters for different teams in every stage, so development, production, staging, all of those. And this is also getting more complicated when you have more than one customer. And so we have different customers that have different installation in different cloud providers, or they are running on-premise. So as you can imagine, there are several problems that we need to tackle. Which are those problems? Well, we have to maintain the state through all these clusters or through all these layers, through all these components. We have to automate these actions. We cannot continue running shell commands to upgrade clusters or to upgrade components. We need to version our cluster, so we will bundle the different components behind a version, and then we will provide an API to our customers to could upgrade the clusters or change the clusters. We also need to provide some observability, so we know when one of the components are not working fine, or when an upgrade is stuck, or something like that. And if we reflect a bit on these problems, they are the same problems that probably you have faced before when you need to run your own microservices platform. And this is probably the reason that you have choose to run Kubernetes. So at some point we decided, OK, then let's go and run Kubernetes cluster to manage the different tenant Kubernetes clusters. So we create this concept, OK? And we have, for every installation that we do, we create a control plane, which is just a Kubernetes cluster. And we run a series of operators that will help us to automate and to maintain the state through the different installation customers and clusters and components. But what is an operator? Well, Jose explained it the first day very well, but I will do a quick review. An operator is a piece of logic that it usually runs in your Kubernetes cluster. It watches a series of events that comes from the Kubernetes API. At the same time, you can extend the Kubernetes API using custom resources. You can create your own custom resource definition. And in this definition, you can define which is the schema of your resource that you want to use. So it's exactly what we have done, right? We have created, for example, for cluster, we have created the cluster custom resource. So in that way, our users can create this custom resource as it will be a deployment or config map. He adds all the specification needed, and they submit it to the Kubernetes API. The operator that takes care of this cluster object will hear this event, like update or create cluster or modify cluster, and it will react. An operator is doing always a loop, as Jose explained it. It's always observing the events that are coming, it's analyzing the current state of the cluster, and it's performing the action based on this current state. It's always doing the same. How it looks like a custom resource? Well, if you are familiar with Kubernetes resources, you will find this schema familiar. We have the API version, which instead of the Kubernetes domain, it has our own domain. We have the type of the resource, which is a cluster. We have some metadata that is the same as other resources in Kubernetes, with the name, labels, and all this stuff. And then we have the spec and the status. The spec is where we will define which cluster we want to create. So with version of the cluster, with components, all that stuff. So this will be our desired state. And in the status, will be populated by the operator when the things, the actions start to happen. So the status will be our current state. And a sample of a custom resource spec that we have two parts, the cluster and provider here. The cluster, you can see some domain zone, some DNS zone, that this cluster is going to be. We have also the possibility to define OIDC parameters, so the users can log into the Kubernetes API in the tenant cluster with Okta or GitHub or whatever I want. We have the provider, which defines specific resources of, in this case, AWS. So the availability zone, instance type, region. And then we have the, no, come on. We have the, no, why? No, why not? Maybe clicking the screen works? Yeah. OK, so we have the status. In the status, here we can see, for example, events that happen related. So the cluster has been created and what time has been created, and also the name or the values of different resources that has been created in the cluster. Then we have not created an operator from scratch and repeat it for every time that we have to create an operator, because we have several operators. So we created an operator kit, which is a set of libraries that help us to do all the boilerplating of the custom resource, help us also to manage certain situations like the deletion of an object of our resource, because there is something to take into account when you do an operator. Also, it helps us to expose some metrics for every operator. But this is our own framework. It's a bit more tied to our necessities. There are some other ones. We have KubeBuilder, which has been created for the Kubernetes community. And we have the operator framework. The operator framework is the last one, but probably is the most user-oriented one. And it's really nice. And indeed, operator framework is a set of different projects. We have the operator SDK, which helps us with the same as operator kit to develop, to boilerplate all these things, to quickly start to code in the logic of your operators. But also, operator framework has the lifecycle manager, which helps to run multiple operator versions against different custom resource versions. So that's a good chance if you want to create your own operator. So this is our control plane cluster. And in the control plane cluster, we have these different operators. We have cluster operator, the provider-specific operator, which here is AWS, and no operator. And these three operators take care of the layers from the infrastructure to the core components. So we have defined this is like a bundle, and they run to manage all the operations related with this one. And we have created a different operator, which is called the app operator. And this one is only taking care of the managed apps. We consider that these have different life cycles, and we need to allow our customers to upgrade or modify one of those without modifying the different ones. So let's talk a bit about the different operators and components that we have in our control plane. We have the API, and the API is a wrapper to the Kubernetes API. The reason why we have been doing it is because some time ago, like 3 years ago, when we started with the project, there was no much functionality in the Kubernetes API like now to, for example, enhance the user experience of the customers. So we can easily let them create a cluster with some defaulting, validating the cluster YAML that they provide. All this stuff is now made by our API. And currently, we are migrating to the Kubernetes API because nowadays you can extend easily the API and make all these functions, for example, using admission controllers to validate or to default all the values, and our users will have more facilities to create clusters or manage clusters. Then we have our first operator in the control plane, which is the cluster operator. And this operator is the one that takes care of all the assets related with the cluster, but the ones that no are provider-specific. So, for example, it creates or manages the creation of all the certificates needed to talk between the tenant clusters components. It also takes care of the versioning of all the core components and other things. And we use Vault to generate all these certificates, by the way. And Then we have the AWS operator or the provider-specific operator, Azure or on-prem operator. And here, the operator, obviously, what it's doing is generating all the resources in your cloud provider or on your on-prem. And it creates all the VPC, subnets, all the resources talking to the, in this case, AWS API. Then we have the node operator. And the node operator is the one in charge of the workers. So every time that, for example, we need to upgrade a cluster, node operator will cordon and drain the nodes to not affect the customer workloads. And as I said before, we are running different cluster versions. So we don't force our customers to always have to upgrade to the latest version. They can select the version, and they can create clusters in older versions to check an upgrade or whatever they want. And at the same time that we are versioning these bundles, these templates of clusters, we are also versioning the operator logic. So we ensure that all the time this cluster is managed by the same logic. So we have not to always run bigger versions being retro-compatible. OK. And we package all of our components as container images. We run everything as container in Kubernetes. I forgot something bad. And then we use Helm for the templating of the Kubernetes resources. I'm going to quickly explain what is Helm or how we use Helm. Helm brings us the concept of chart. A chart is the package that will be created to deliver your application in Kubernetes. And it has these three different files or folders. The first one is the chart YAML, where we have all the package metadata, the name of the chart, the version of the chart, the version of the application behind the chart. And then we have a templates folder where all our Kubernetes resources are. Helm allows us to use contemplate to parameterize the different resources. So thanks to the values YAML, we can set some parameters, and they will be populated into the Kubernetes resources. And when you use Helm to install or upgrade your components, you can supply the values YAML that you want. So you can use different values YAML for different environments or different clusters. So we are using this currently. And our release process will be something like that. In terms of the control plane operators, we have a platform designer. He made a feature, or he fixed a bug, and he pushed the code to the GitHub repository. Someone make the review and accept the chain. So it is merged. It is building a trigger building to CircleCI. CircleCI run a series of unit tests. And so we are running some series of integration tests. So we ensure that from one version to each other, nothing breaks. We don't have any regression. And when all is green, the CircleCI is pushing the container to our registry. In this case, it's Quay. And at the same time, it's creating the chart. And it's pushing the chart to Quay. When it is done, it generates a deployment event to the GitHub API. And for every contemplate cluster, we run an agent, which is called Rotsman, which is watching the GitHub API. And when there is a new version of the operator, it takes the version and pull the chart from the chart repository, and then install this new operator like another Kubernetes, like a Kubernetes deployment you will do with your application. And then we have created the release bundle, which is the logic set of all the components that we run for a template of a cluster. All of them are version. We provide as well Chainlock with the difference between one version to each other, to the next one. And we have also a status of the release, because we always have a work in progress release bundle where we are shipping all the features, all the patches, until we officially release one of these cluster templates. And then we have also the release date. So this is how it looks like. We have some metadata, the version, the date, if it's active or not. And the interesting part is the components, because you see here that we bundle together the AWS operator along with the container network, in this case Calico, along with some core components like cluster autoscaler, the etcd database value database is also there, the Docker version, so everything is version. That way we ensure to our customers that if you create the version 7.0.0, it will looks like the same, and it will be managed always the same. And this is an example of a Chainlock. So we expose all the changes that has been done from the previous version. And some occasions where, for example, we update Kubernetes, we provide a link to the release info page. So this is the different operators that take care of the main core components and the below layers. But we have developed the app operator to manage the managed apps. How does work? Well, we have our solution engineer or our platform engineer that wants to create a chart, an application. And so he makes the chart, or he took the chart from the community. There is a good catalog open, so you can get for most of the tools or frameworks like a default chart. Then you can start to chime in and changing things for your case. And when you have finished, you can push to the app catalog, which is just a Helm repository that we run in GitHub. And then this operator, what it's doing is creating an app resource. This is another custom resource that we run. And the app resource looks like this. We have an API version, like we have it for the cluster. And in this case, it's not anymore core Junction, it's application Junction. We have the app type, some metadata. In this case, the name of the application is Stana agent. And we have some spec. And here in the spec, you will see that there is a reference to the catalog, because you can have multiple catalogs. And you have also the config map. And this config map is the values that is going to be applied when the app is installed. So you can have a chart in your app catalog, and you can create multiple instances of app, each of those with different values YAML. So it will be configured this app differently. And at the same time, you have to provide a kubeconfig. The kubeconfig is the credentials of the cluster API where you want to install this application. So you can run, for example, in your local and Minikube, the app operator, and you can point them to your production cluster and install an app thanks to this resource. We have the name too, and the namespace where it's living this app resource and the version of it. And also we have a status. So the app operator is populating the status with the latest information of the current state of your application. In this case, has been deployed, which version of the app is running, and the version of the chart. So I told you a lie, because the operator is not really installing the chart into the tenant cluster. What he's doing is creating a chart custom resource. And we have another operator, because we like to build operators. And this chart operator will take this chart resource and install the chart into the cluster. But why the app operator is not really installing? Well, because we think, or we like to think, that we follow the single responsibility principle. So an operator only does one thing, and it does fine. And in this case, the app operator has to configure the application and have access to the cluster and validate that the configuration is good. And then it produces a new custom resource So someone else, in this case, a chart operator, will be actually upgrading or installing this chart into the tenant cluster. So this is how it looks like the chart resource. We have, again, API version, we have the type, we have some metadata. And here, the spec is a bit similar to the app. But if you see, there is a tarball URL, which is really the package that has to be installed. And also, in the config, you will see that now there is a config map, and there is also a secret. So when you define your ARP in your chart, you can want to hold some sensible data, like a credential token, password. So you can create it in the config map of the control plane. And then when the operator creates the chart, it will create two different resources, a config map and secret, and the secret will hold the sensible data. So we don't expose this, or we treat the data accordingly to the Kubernetes good practices. And then we have here the same status that we have been watching in the app. Indeed, this status is populated to the control plane. So I'm talking a bit more to close the circle about the observability. So we have in the control plane cluster, next to the operators, a monitoring stack and a logging stack. These are connected with all the tenant clusters in the installation. And how it looks, the monitoring stack is nothing really, really fancy. Probably you have heard of all those projects. But we are running the control plane, a Prometheus server. So it's a time series database server which scrape. It has this pool approach to scrape the metrics for the different tenant clusters. And in each of those clusters, in each of those tenant clusters, we are running a series of exporters, which is just a small, tiny piece of logic which is taking information from different areas. So we have a node operator which takes the metrics related with the CPU of the host, the memory, file descriptors, a lot of things. We have the net exporter that we have built, and it is checking that the network layer is looking good, there is no errors. We have a cert exporter, which looks like the certificates, all of their components are not expired or are not going to about expire. And they expose these metrics, so the Prometheus server is able to scrape the metrics and gather all the information. But as we are creating tenant clusters dynamically or removing, this configuration has to be updated. Prometheus needs to know when there is a new cluster created. So again, we have created another operator. And in this case, it's more a controller because it doesn't have a custom resource. But this controller is hooking into the API of Kubernetes. And when he detects that there is a new cluster resource, he will populate the configuration of Prometheus with the new endpoint of the end cluster, and it will reload the Prometheus server. So that way, it will start to scrape from the exporters in this cluster. We are running a Grafana with some dashboards that help us to see what is the status of the different tenant clusters. So we have one Grafana for all the installations. And we can filter by cluster, by namespace, and we can see if something happens in a managed component. And then we have the alert manager. So we produce a series of rules and alerts in Prometheus. And when there is something that is not working well, we have connected this alert manager with Slack and with Opsgenie to wake up or notify the on-call engineer on duty. So we have the observability part of the logging part of the observability, and again, nothing fancy, but we have our Kibana, Elasticsearch, in this case, Fluent Bit, running here, and Probably most of you know FluentD, which is a great product, but it requires a big footprint in terms of resources, and we don't want to take much of the resources from the tenant clusters of our customers, so we prefer to use FluentBit, which is smaller, and it is enough for us. So these FluentBits are forwarding the logs of our managed components to the Elasticsearch. And then we run also some jobs, some creator jobs, so the index are removed or parsed, and all this stuff. And then we run Kibana on the top, so an operator can always check the state of one of these components in the clusters. So yeah, takeaways about the talk. If you are running Kubernetes, leverage on the Kubernetes API, because it's great, and there is a lot of possibilities nowadays to extend this API. And Kubernetes is quite good producing the documentation. Operators for the win. So what we have found between our customers is at the beginning they are really wanting to create operators, because this is more like not the area of control that they want to have. But at the end, there are a lot of ways to do it, and I talk about the operator framework, which you can easily start to code your operators. Even you can use other languages, not only Go, which is the official language. You can use also Python, and create your operator to manage specific applications that are running in the top of your clusters. And also the separation of life cycles. So yeah, it's good to know which, if you're running Kubernetes to create like a PaaS, like a platform as a service, you will have probably more than one layer, and you have to see how to manage these different life cycles of the different components through the different layers. So thank you, and thank you also to my second family, these guys. And yeah, if you wanted to ask me something, I'm open to respond.
Questions?